Hey everyone, today we're diving into Agentic AI, the kind of AI that doesn't just answer questions, but plans, decides, and acts over time. If you want to build smarter assistants, autonomous robots, or robust decision-making systems, this episode will give you a clear step-by-step map. Stick around. I'll walk through the architecture, components, a practical implementation plan, and safety checks. Let's start with a clear definition. An agentic AI is an autonomous system that perceives its environment, maintains internal state or memory, reasons and plans across multiple steps, takes actions, and learns from outcomes. Think of it like a small decision-making brain with sensors, thinking layers, and actuators. At a high level, agentic AI typically has 5 interacting components: sensors and perception, a world model or knowledge base, a reasoning planning engine, an action executor, and a learning module. These components communicate in loops. Perception updates the model, the planner selects actions, the executor acts, and the learner updates the model and policy. Perception is how the agent ingests data. This could be text, sensor streams, images, or structured telemetry. The goal is to convert raw inputs into meaningful representations: tokens, embeddings, symbolic facts, or state vectors. Robust perception pipelines include preprocessing, filtering, and uncertainty estimates. Next is the world model or memory. This can be short-term working memory for active planning and long-term memory for facts and learned dynamics. Architectures vary: symbolic knowledge bases, vector databases, transformer attention memory, or learned dynamics models. The key is accessibility and reliability for the planner. This is the agent's thinking, reasoning, and planning. Approaches include classical planners, model predictive control, search, Monte Carlo tree search, and neural policy networks. A common modern pattern is using a large language model or planner to propose high-level steps, then grounding those steps with specialized modules and cost estimates. Execution turns plans into real actions. For software agents, this might mean API calls, database updates, or message sends. For robots, it means motor commands and control signals. Executors need safety checks, rate limiters, and rollback capabilities to avoid catastrophic mistakes. Learning lets the agent improve. Supervised updates, reinforcement learning, online continual learning, and offline policy distillation are common. An agentic system often uses reward signals or human feedback to refine its planner and world model over time. Safety is crucial. Techniques include constrained planning, red team testing, interpretability checks, out-of-distribution detection, and human-in-the-loop overrides. You should instrument agents with audit logs, approval gates for risky actions, and verifiable specifications for critical tasks. Let's run through an example flow. 1. Perception detects a new customer request. 2. World model fetches context. 3. Planner drafts a multi-step plan. 4. Executor performs safe API calls to fetch data. 5. Learner updates policies based on success metrics. This loop repeats and refines. If you want to build one, here's a practical checklist. 1. Define specific objectives and constraints. 2. Choose perception modules. 3. Pick a world model type. 4. Implement a planner with simulation testing. 5. Build a safe executor with rollbacks. 6. Add learning with metrics. 7. Put monitoring and human oversight in place. Start small. Iterate fast. Here's a high-level pseudocode sketch. Loop. Observe, update state. Plan equals planner state. Safe plan equals safety filter. Plan. Execute safe plan. Record outcome. Train on outcomes. Keep modules decoupled, so you can swap planners or perception models easily. Measure success with task completion, efficiency, safety violations, and calibration of confidence. Use unit tests, integration tests, simulated environments, and staged rollouts. Benchmarks and replay buffers help reproduce failures and improve reproducibility. Agentic AI is powerful but comes with real risks: unexpected behaviors, reward hacking, privacy exposure, and misaligned incentives. Ethical design, transparency, and legal compliance should be part of the development lifecycle, not an afterthought. Real-world uses include customer support agents that autonomously resolve tickets, industrial robots coordinating complex assembly, personal assistants that manage multi-step tasks, and research agents automating experiments. Each use case requires tailoring the safety and evaluation layers. If you want to get started, read papers on autonomous agents and RL, experiment with vector DBs and transformer planners, try simulated environments like OpenAI Gym or Habitat, and follow safety frameworks from major AI labs. I'll drop links and resources in the description. All right, that's a wrap. If you found this useful, hit like, subscribe, and share. Tell me in the comments which part you want a hands-on tutorial for: perception pipelines, planner internals, or safety testing, and I'll build it. Thanks for watching, and see you in the next deep dive.